The question type is actually kind of a bit of the same also. It's just that we have a different manipulator, and then have some changes on the task. So after today's lecture, I believe all of you can start on your CA. So we are going to have a quiz as well. So the quiz so after today's lecture, I'll upload the exercise 3. So you can actually practice on the exercise. Then next week, I'll release the solution for exercise 3. So the exercises are not graded. And then after that, I will release a quiz, an online quiz. So the online quiz is actually very much similar to the exercises. So we actually provide you with some practices. Okay. We wait a while more before we start the lessons. So if I'm going too fast, please let me know. If you can't hear me, please let me know. So today will be the last lecture for this part of the module. I think we are not going to have a makeup for the New Year lesson, for Chinese New Year lesson that we missed. Okay. Any questions? Sorry. Sorry. How many questions in the quiz? So the question have multiple parts. Yeah. So probably will be about not more than 10. Yeah. No more than 10. Yeah. You have 2 weeks to work on the quiz question. It's a practice. It's a rehearsal. Because every time for the exercise, I actually find that a lot of you will actually wait for the solution to come to you. Then you actually look at the solution, and then for the exercise. So maybe take it as a quiz so that you can actually have more motivation to try solve the problem. Yeah. Sorry? No, structural question. Most of them will be structural questions. Structural question meaning that you fill in the blank. I try to make it straightforward so that you only need to give an answer. I will guide you through the question will actually kind of like guide you through the process. Yeah. So it's not difficult. Yeah. So don't be worried. But I guess it's a good motivation for you to actually go back and revise, and then try solving the problems. Yeah. No worry. Yeah. So usually the quiz and the CA will help you. And then CE will kind of actually prepare you for the final exam also. Right. So if you're only attending the lesson itself, you probably will be you might not be able to really learn from this course. So even though this course is actually a theoretical course. Sorry? You can work on the quiz. It will be open for 2 weeks. It will be open for 2 weeks. So you can do multiple attempt, and then you can do multiple attempt, and then you should select your best attempt. Yeah, but please don't for one single answer try multiple times. Yeah, just to Okay. Yeah, it's open for 2 weeks. Yeah, it's longer than last year. We only give the student 1 week. But I guess, we have. I guess this time we give away 2 weeks because so that all of you can have more time to prepare for it. Can? Yeah. Okay. Yeah. Don't worry about the quiz. Don't worry about the CA. So they're meant to help you to actually know the subjects. Okay, so don't worry about these slides. So I actually get this revision slide up to date, so I'm not able to send to all of you. So I will upload it after the lesson. So try to focus and listen to me. Okay, so I guess in the very first lecture, I've told everyone that this module is actually about the classical robotics. So meaning that it's the study of the industrial robotic manipulator, which is an integrated approach of kinematics, statistics. So we have been looking at kinematics, and then we are almost done. We are going to do statistics later after this. And then after that, we are going to do trajectory planning as well. We did talk about the physical hardware, but we actually covered the physical hardware in chapter 0. So we don't. So obviously, the physical hardware is not really the focus for this module. I think I mentioned that in our first lesson. So in the second half, you will learn about the dynamic as well as the control strategy. So the advanced robotics is essentially a theoretical analytic course. So I'm actually expecting you guys to have some background knowledge. So previously, we actually expect the student to have taken the module called linear systems. But we don't think that is actually necessary, because not all the things that you actually cover in linear system is actually applicable here. But you should be comfortable with linear algebra. And then on our first lecture, I actually have some slides going through, have a quick review on the linear algebra. And then there's also a PDF called Linear Algebra Review that actually covers a bit of it. So you should be comfortable with linear algebra, and then actually I'm expecting everybody by now should have gone through these two slides. The slides 66 to 76 of the chapter 0, as well as the linear algebra review. So you should know the trigonometry, so all the cosine rule and all those sine, cosine, and all those stuff. So you should know. You don't have I guess, but so we have this trigonometry identity.pdf. So basically this it's just one sheet of paper, so it doesn't actually require you to know that many. And then you should be familiar with MATLAB. So at the end of the day, we still need to do a theoretical analysis of the module. So I'm not expecting you to use pen and pencil to do all the derivation all the time. So the MATLAB is actually quite useful for you to derive the mathematics. You'll find it useful, particularly the symbolic max toolbox for the assignment. And then so you should actually download the software, experiment, try out on your own. There's also a robotic system toolbox with MATLAB. So these are something that I'm expecting all of you should have achieved. And then the first topic that we actually focus on, the first thing that you actually need to know is homogeneous transformations. So the homogeneous transformations is important to study the kinematic of a manipulator. So for example, if we have a manipulator, so this simple manipulator here, and then this is a particular point P. So this is a particular point P. You want the manipulator to actually pick up this point. So the consecutive transformations is a set of actually the mathematical tools that you actually use to study the kinematic of the manipulator. So what you did is actually you assign a frame to the length of the manipulator. So for example, you have this frame 0, frame 1 to frame n-1, and then this is the frame n is typically your n effector, and then you have this point P that you're actually going to target, you are going to focus on. So when you have so for example, if you are given, you have given MP, MP over here meaning that the point P is actually we refer to your frame M. So the M over here is your referencing frame. So if I have, you are given the MP, the point that you have to target, we refer to your N effector. if you are also given the transformation matrix. So the transformation matrix will always be written is I minus 1 I. So what this means is actually I referring to I minus 1 frame, or I with respect to I minus 1 frame. So this is homogeneous transformation. A homogeneous transformation meaning that it's a 4x4 matrix. And then it's a 4x4 matrix comprised of a rotation matrix, a 3x3 rotation matrix, and then a translation vector followed by an additional row, the fourth row. So with that, you want to find the point P, we refer to the base frame of the membrator. So in most cases, we actually assume the base frame to be a fixed frame. So this is the base frame. And then, so the consecutive transformation will actually allow you to say 0P is equal to 01A, 12A, n minus 1A, A, and P. So this is essentially your ONA and P. So if you can visualize it as something that you can cancel off the 1. So the lower subscript cancel off with the upper subscript of the next matrix. You will actually end up with 0 and A. So meaning that this is the transformation matrix of M, we refer to 0. So you can simply 0, 1A, 1, 2A, n minus 1A is equal to 0, 1, 0, n A. So this is the consecutive transformation. So we now we know that we actually need to, in order to achieve the task that we have, we need to assign the frame to the manipulator, to the frame, to the length of the different manipulator. So the question here is, how can we do that? So we do that using something called DH notations. So we generalize a manipulator as an open kinematic change. So for example, so in this open kinematic change, we have the base frame. So the base frame is fixed. So this is a base frame. So you have your OO, XO, YO, and ZO. So they are represented in a right-hand coordinate systems. So right-hand coordinate system meaning that if you move from X to Y, if your finger curve from X to Y, the thumb will actually give you the Z. So you have the base frame, you have the N effector frame. So this is your N effector frame M. This is known as an open kinematic chain. Essentially, it's a serial link. So we want to express the N effector position and orientation with respect to this base frame. So using the tools that we have gone through with the homogeneous matrix. So the DH notation represents a systematic method of describing the kinematic relationship between a pair of adjacent links in the open kinematic chain. So it's based on the 4x4 homogeneous matrix representations. And it actually uses a minimum number of parameters to describe the kinematic relationship. So there are many different variants of DH representation. The one that we actually go through in class is called the classical DH representation. So this is the classical DH representation. So over here, we consider a link. So we consider a joint I, and joint I is actually attached to joint I minus 1 via the link I minus 1, and attached to a joint I plus 1 to link I. So the first thing that we actually need to do with the classical DH representation is to attach the frame. So you have to find the origin of the I coordinate frame, OI. So it's actually supposedly located at the joint axis I plus 1 and the common normal between the joint axis I and I plus 1. So this is the joint axis I plus 1. And then this is the common normal. So with the joint axis and common normal, you define the origin OI. So this is for link I. So you have this over here. And then after that, you need to determine the XI axis. So the xi axis is directed along the extended line, extension line of the common normal. So this is the extension line of the common normal. So you have your xi. And then after that, you have your zi. So this is from what being described as a classical DH representation. So when you have the xi and zi, you can find the yi because of the right-hand coordinate systems. So the y-axis is actually chosen such that they form a right-hand coordinate frame. So from x to y, you will have your z being pointed out in this manner. So you attach the frame. Then after that, there are essentially 4 parameters to determine the relative location of the frame. So you have the angle between the xi minus 1 axis and the common normal HIOI measure about the zi axis in the right-hand side. So you have your theta I. And then you have the distance between the origin OI minus 1 and point HI. And then you have the length of the common normal. And then finally, you have this alpha I, which is at the angle between the joint axis I and the z axis in the right-hand side. So you have these 4 parameters. So if I'm to summarize this into a set of rules, I will illustrate it using an example. So for example, before that, I can represent. I may take out this nice drawing of the link, and then we only look at the skeleton. So this is a frame OI minus 1. This is a frame OI, and then you can actually see that there's actually an intermediate frame over here. So the intermediate frame provide you with options to actually link the two together. So the intermediate frame, intermediate frame IA, we actually refer to the frame I, we refer to the intermediate frame, is given by a homogeneous metric over here. And then you have this other frame, which is your I minus 1 intermediate frame A, another rotation matrix, another homogeneous matrix. So your I minus 1 I A is essentially equal to your I minus 1 intermediate frame A, intermediate frame I A. So when you multiply these two together, you actually end up with this transformation matrix. And this transformation matrix is actually applied across for all I minus 1 I A in classical DH notation. So this is a method, and then we have illustrated it using a simple manipulator. So we have illustrated a simple manipulator, and then we have illustrated with a more complicated 6 degree of freedom robot in the lecture note. So we go back to this simpler manipulator. So this simpler manipulator is a RR manipulator. The word RR over here refers to the revolute. So you have 2 revolute joints. So you have 2 revolute joints. This is the first revolute joint. This is the second revolute joint. And then the first thing here is you are going to attach the frame. So we have gone through the definition of the frame as per the DH notations. And then they can actually be translated to these 4 DH frame rules. So there are many different ways of interpreting the rule. So this is one way of interpreting the DH notation, the classical DH frame attachment. So the first thing is you look for the z-axis. The z-axis is essentially the axis of the revolution or direction of the motion. So you know the joint. You know the axis of the revolutions. So it's a single degree of every joint we have mentioned that every robot basically consists of all one dimensional, 1 degree of freedom joint. Okay, So you have this 4-frame set of rule. So the z-axis is the axis of revolution or direction of motion. So you can easily define your Z0 over here. And then the x-axis must be perpendicular to the z-axis of the previous frame. So you have this Z0, you have this Z1. So this Z1 is this is the angle. Then you can, the x-axis must be perpendicular to the z-axis of the previous frame. So this probably will be, this is your x1. And then x-axis must intersect the z-axis of the previous frame, so you actually expand out. This is where you actually extending. And then from there you can actually simply draw your right-hand rule. The base frame and the end effector of those is actually considered as a special case where you can actually kind of set arbitrarily. But you will always try to do it in such a way that you can actually minimize the number of variables. So meaning that on the final table, you want to have as many zeros as possible. So if you look at this itself, we'll actually kind of think that your XO will probably be perpendicular, will be in the same direction as this. So you have your XO. So you have your XO, ZO, you can actually do your YO. And then finally, same thing, this will be easier if your x1 continue to be your x2 over here, this perpendicular, this being parallel to it, and this is your y2. Okay? So this is the 4DH frames rule. So basically you need to have, if you actually look at exercise 2, you will see that the exercise 2, the first 2 questions are essentially how you putting on, how the exercise on attaching the frame, forming a DH notation, and so on. Then after that, you need to form the parameter table. So the parameter table, again, you have this theta, alpha, A, and D. So the theta is your angle of rotations. So basically, you can actually define it as the angle between the xi-1 axis and the common normal HIOI measure along ZI-1 axis in the right hand side. Basically, if you go along this ZI-1 is the rotations from your xn-1 to Sn. Okay, and then you also have your alpha, and then you have your A as well as your D. So we look at the theta. So if you look at the theta, if I move from x to x1, the initial resting home positions, you have the angle 0. But this is a variable itself, so you have 0 plus theta 1, which is actually equal to theta 1. And then the second one is theta 2. Okay? And then with that, you can actually form the DH parameter table. We have gone through this example. Yeah. There's also a modified DH notation, but this is for your information. When the second half starts, the second half will probably, the part 2 will actually, when you talk about the dynamic, they are going to use a DH, the lecture is going to use a modified DH parameter. So you will be taught the modified DH parameters. They are essentially the same. The method is essentially very much the same, except that they have a different set of parameters. So you have your A, alpha I minus 1, AI minus 1, DI, and theta I. So this is, so the modified DH parameter is also the one that's actually been presented in the textbook, being given in the textbook. And then after that, so once we have the DH notation, and then once we have the intermediate frame, we can put everything together, do these consecutive transformations, and what you have is a forward kinematics. Yes?
Why do it have this modified DH parameter? What's the difference? Like, is there anyone that is better than the others? How it works?
Modify.
The notation is also different.
Yeah, the notations is so for the modified DH notation, it basically from your link I to link I minus to link I plus 1. So it's a variant of the classical DH notation. To say which one is better, which one is not as good, I guess both have I would say both have disadvantage and disadvantage. Classical DH notation will be better if you're actually doing the classical analysis. Yeah, so this is why you should know both. Yeah, so beside the classical DH notation and modified DH notation, there are other variants of the DH representation as well. Okay.
I thought it's more like two systems, but which one is more commonly used than the modified DH?
Okay, so which one is more commonly used today? Both are equally used.
Thank you for that.
Yeah, both are equally used. I mean, both are equally commonly used. So of course, now the textbook, the textbook is actually pretty popular. So modified KH notation is actually being taught in undergrad robotic class more. Yeah, so the classical DH notation is more for advanced class. Okay. So because the advanced class, we also tend to fall back to more analytical analysis. Okay, so we form the forward kinematic after we have the DH representation, and then the next thing that you actually need to know will be the inverse kinematics. So the inverse kinematic meaning that if you are given the n effector position and orientations, you are supposed to find the joint displacement. So for example, in this case, you have geo nt. So this is your n effector position and orientation. You are supposed to determine the joint positions. So your ONT is essentially a multiplication of your consecutive transformation. So you have your O1A, Q1, 1 over 2A, Q2, and so on. So in between every one, this is your intermediate, your transformation matrix, which is I minus 1 I, A, cosine theta minus sine theta I, sine alpha I, and so on. So this is the transformation matrix that we have derived earlier. So the solving of the inverse kinematics probably isn't quite a DH representation that can actually achieve it. So it's actually involved basically is a general analytical method. So the general analytical method meaning that if you expand out the forward kinematics, so this is the forward kinematic equations, you actually isolate one joint variable at a time. So for example, if I multiply 0, 1, A minus 1 to the left-hand side of the equations, of the kinematic equation, it will be multiplied on the right-hand side of the kinematic equation as well. So what happened here is you will actually end up with something like this. And then the right-hand side become 1 over nt. So this 1 over 1 nt is essentially a function of q2 to qn. And then after the step involved, basically you look at the constant element in 1 over nt, and then you try to equate the left-hand side with the right-hand side, and then you solve for the q1. So basically you solve one at a time. It's an analytical method. There's actually no step-by-step algorithm that actually like the DH representation to do it. But it does have some approach. So there's no algorithmic approach that's 100% effective, and then a lot of time we actually have to look at the geometric intuition. So you look at the geometry of the robot manipulator, and then from there we actually try to find a way to simplify it. So one specific method we actually highlight is something called kinematic decoupling. So we use so this is from from the Asada book. So this is from the old text, another textbooks that we refer to in this course. So in this books, it's actually used an example of a 5R 1P manipulator. So the 5R over here refer to the 5 revolution joint. So this is 1 revolution joint, second, and then you have 1 prismatic joint. So 5R 1P. And then over here you have an effector. And then this is the width. So one way of doing it is actually via something called kinematic decoupling. So kinematic decoupling meaning that we divide the inverse kinematic problem into 2 parts. So the first part will be, we actually identified the width. We have gone through in the class also with a different example. So we identify a width, and then we find the coordinates of the width center points. So you calculate from here to here, you calculate. And then after that, you find all the joint angle behind the width center point. So meaning that you take this as a center, and this to determine this, and then after that, then you determine this. So we break them into two problems and isolate them, rather than isolate all the 6 degrees of freedom altogether. So the kinematic decoupling is easier. It simplifies the problem, but it doesn't apply to all the manipulator. Okay. Sorry? This is for you to find out. Yeah. Okay. So after that we look at the after we go through the inverse kinematics, inverse kinematic, we went on to study the differential. And then the main thing, and one important thing that we actually need to know is a manipulator Jacobian. So the manipulator Jacobian, we have gone beyond looking at the position and orientation of the n effector and the joint. We want to study the relationship of the velocity. So the velocity at the n effector with the velocity at the joint. So same thing, you have to start from the forward kinematics. And then we actually derive that if when we compute this manipulator Jacobian, we actually assume a very small movement. So this is the infinity n effector translations and the infinity n effector rotation. So you have your dp equal to dxe d phi e. So you can write this as P dot VE omega E. So this refers to the n effector. And then the n effector velocity. And then the Q dot over here is actually referred to your joint velocity. So you have your Q1 dot, Q2, Qn dot. So every one representing one single joint, the velocity of one single joint. So the manipulator Jacobian will actually link the P dot equal to JQ dot. So what is actually contribute? What is actually contributes of this manipulator Jacobian? So the manipulator Jacobian will comprise of 3 rows that actually representing the JLI, and 3 rows that actually representing, and the bottom 3 rows is representing JAI. And every column itself is representing one single joint. So meaning that you have 6 by n, so Jacobian matrix is a 6 by n matrix. And then if the joint is actually happens to be a prismatic joint, the JLI, JIA will be equal to BI minus 1, 0. It's a prismatic joint, so there will not be, you don't have anything, you don't have any rotation, you don't have any torque. And then if it's happened to a revolute joint, your JLI, JII will be equal to the BI minus 1 cross RI minus 1 E, and the JAI is equal to BI minus 1. So bear in mind that the Jacobian is configuration dependent. So the configuration of robot actually play a part. You look at we continue with the RR manipulator. So if we, based on what we have gone through over here, we can form a table like that to determine the Jacobian matrix. So this is the linear portion. The linear consists of 3 rows. The rotations consist of another 3 rows of the Jacobian matrix. And if the column representing a prismatic joint, you have your Pi minus 1. Your Pi minus 1 is essentially equal to your 0I minus 1 R 0, 0, 1. So when you multiply by anything by 0, 0, 1, meaning that you are essentially only picking up the third row of the rotation matrix. And then for the rotation part, the prismatic joint is 0, so meaning that all the 3 elements are 0. The revenue joint, you have your Bi minus 1 cross Ri minus 1E. So if you actually expand it out itself, it's actually equal to your Ji minus 1 R 0, 0, 1 cross Dn minus 0 I minus 1D. And then your Bi minus 1 is your Bi minus 1, which is the third row, which is the third row of your rotation matrix. So once you have this table, you can then start forming the Jacobian matrix. So you know that this is the n effector. This is the n effector velocity, and so you have your s dot, y dot, z dot, omega s, omega y, omega z. This is actually representing the n effector. And then for this RR robot, there's only 2 joints, theta 1 and theta 2. So theta 1 and theta 2, so you have your theta 1 dot, theta 2 dot. So there are 2 revolute joints. So this is a revolute joint, this is another revolute joint. So you look at this, and then you copy it over here. So after that you look at the first one, you will be 0, 0, R. The first one 0, 0, R. When you have 0, 0, R, basically you have an identity matrix. So you have your identity matrix, so it's 0, 0, 1, then you cross your 0, 2D minus 0, 0, D, and then you form the transform. This is essentially your transformation matrix from your forward kinematics. So with that, you can actually form your Jacobian, and then from here you can actually see that they are altogether 6 equations. So your S dot is equal to this multiplied by this. The first column, the first row of this multiplied by this. And then the first row of these 3 elements of this multiplied by your Q dot. So you form these 6 equations altogether. The Jacobian does give you some interesting, from the Jacobian itself, it actually gives you some interesting observation. So like for example, the omega z is equal to theta 1 dot. So meaning that your n effector rotating in the z axis is basically only depending on your theta 1 dot. Okay. So this is a run through of what we have gone through. It's a matter of familiarity, so after a while you will be familiar with it. I'll upload the slides. Yeah, so I'll upload the slides. So if this happened to be your first time attending a robotic course, you might find it a bit unfamiliar. So you need to revise. Yeah, and then I presume after the quiz, after you did the CA, you should be relatively ground in the kinematics of the robot. Okay, so this year CA is actually kind of different from last year CA, the previous year CA. So the previous year CA, there's actually comprised of a few questions, and then so this time around, we only focus on one robot. We only have one one questions, but there are actually multiple parts, like what in the previous CA. So the previous CA is actually deal with a robot called Puma 600 robot manipulator. So this is a Puma 600 robot manipulator. So you can actually see this is a base frame. This is a joint 1, 2, 3, and so on. This is the width. So in this case, from here you can actually definitely observe from the geometry itself. You know that if you are tasked to look for the invert kinematic, you will be able to use the kinematic decoupling. Okay, so this is a Puma 600 robot, and then you are supposed to. So from here itself, the frame is actually attached. So this frame is actually attached in the classical DH notations, and then you have your classical DH notation representation given over here. So the first, you don't have you have the frame attached, so you have to derive the DH notation, the DH notation table. So this is from the student. So the student actually come up the DH representation table or parameter table over here. So you have your AI, alpha I, DI, theta I. So after that you need to do the first question is actually you are supposed to determine the link parameter. So these are the link parameters, and then derive the kinematic equation of the robot. So once you actually attach the frame to determine the link parameter, is actually quite straightforward. You have this I-1 IA, so you have this kinematic matrix. So the kinematic equations actually refer to the forward kinematic equations. So meaning that G06T equal to G1A, G01T times 112T times 23T times 34T times 45T times 56T. So this is actually equal to a matrix. So the matrix will comprise of the rotation matrix. So this is the rotation matrix. This is the translation matrix. You have one additional row. This is a homogeneous metric representation. So every nx is represented over here. So it's a lot. Actually, if you do the calculation, you multiply all the metrics in this manner, I think I'll get mad. If you actually want to do it manually, it's going to be very tough. And then you will definitely make mistakes. So you can actually use something called a symbolic map toolbox. So what the student did is they use a symbolic map toolbox. So they define all the different symbols. And then this is the TB. This is a transformation matrix. This is the table, the parameter table where you have your AI, alpha I, DI, and theta I. Then after that you form all the intermediate transformation matrix. And then you do a multiplication together. The MATLAB will actually do it for you. And then some students will actually go one more step to actually simplify them. Okay? So you are going to do this for your assignment. But in this case, you have a UR robot, a UR5 robot. So in the home position, you do the same thing. The frame is not given to you, so you have to attach the frame. So there can be more than one solution, depending on how you actually attach the frame. And then after you have attached the frame, according to the classical DH representation, it has to be based on you form the link parameter table. So you create this link parameter table, and then after that you compute the forward kinematic equations. So this is the first step for your assignment. Follow so far? Okay. So this is actually a practice of what you have learned. So this is, you can actually read up on the symbolic map toolbox from here. So the toolbox is actually available to you. And then come the inverse kinematics. You need to do the inverse kinematics as well. So the inverse kinematic, you will start from the home position of the robot. So you should know what is the home position of the robot. So home position meaning that is the start position of the robot. So your question is already give you the start position of the robot. And then you specify the point to reach. So in this case, the student specified this point to reach, and then this is the transformation metric 0.60 of that particular to reach that particular point. Okay, and then with that same thing, so obviously you can see from this robot that you can actually consider a width. So you can actually perform the decoupling. So the student do the decoupling, solve the set of mathematics, and then they determine all the joint angle. Okay. So you need to do that. So the previous CA also have a question tree. So the question tree is another configuration of a Puma 600 robot manipulator. So instead of ground on the floor, it's actually hang on the ceiling. So it's hang on the ceiling, and then the robot is actually holding on to a tool. The tool is actually on a workspace. So it's actually on a workspace. So it's supposed to derive the 6x3 Jacobian metric associated with the relationship between the joint displacement and positional orientation of the point A. So you start off with the forward kinematic equation, and then from there you can actually determine the Jacobian. So the part 2 actually require you to determine the force and moment act on the two tip. So you represent the force and moment by 6x1 vector, and then you're supposed to derive the equivalent joint torque. But this is not required in your CA. But this is something that we'll be going through later on. And then the task actually require them to draw a circle. So in your case, you don't have a fixed table, you don't have to worry about the force, but you need to draw in the air or any surface of the different nectar representing flow. So same thing. So in this case, if you want to draw a circle, you probably need to have some waypoint or y point. So you have your A, D, C, and D. So for every point, you need to determine using the inverse kinematics. So after you have determined the inverse kinematics of this point, you need to generate the trajectory to actually link them up together. So bear in mind that you actually need to reach the point, need to coordinate the motions. So this is what the student did. They identified the coordinate of A, B, C, and D, and then perform the inverse kinematic for every point, and then generate the trajectory between the point. We'll talk about how the trajectory can be generated in the later part of this class. So today is the last class, so I have to finish all these things. If I'm going too fast, please let me know. So this is the result of the student. So they specify the 4 point, and then they try to draw the circle, but it doesn't really. It's not really a horizontal circle. So there are some problem here and there. It's actually because of the configuration of the robot, because it's actually fixed on the ceiling. And then this ground and this ground itself are essentially kind of have a certain length, certain height. So it's actually placed a certain constraint. So in your case, you shouldn't have this problem. So you should draw the 4 letter. You should do a plot like that. You should also plot the velocity, the angle. So this is the angle of one of one using the student implemented a cubic polynomial function that we will go to afterward. And this is the angle, this is the velocity, this is the acceleration of the specific joint. Okay. So this is what I'm expecting from you guys for the CA. Okay? Everyone can start now? Can start on the project now? No, it's actually a reflection of all the, an application of all that you have learned. I mean we are going to, I still have two more topics to actually go through. Okay? Okay? So that basically sum up all that I want you guys to know. All the basic things that I want you guys to know. There are actually quite a lot of things like redundancy, mapping, and so on. So there are theoretical things that is good to know if you actually do robot. If you decided to pursue research in classical robotics. So these are some mathematics that you probably good to know. Okay. So now we actually move on to statics. So we have gone through, so I talk about the Jacobian matrix. So essentially the entire chapter 2 is about the Jacobian, the manipulated Jacobian matrix. So we say that the Jacobian metric can actually relate the force, the velocity of the joint with the velocity of the n effector, and then. So actually now we actually move on to look at how the Jacobian is going to relate the force, the n effector force with the joint torque. So this has practical meaning. So meaning that for example, this pendant robot here is operating on a surface. So it's actually applying a force on the surface. So you assume everything at equivalent. So when we mean at rest, we actually refer to a state of equivalent. So you have your F is equal to Fx, Fy. So this Fx, Fy actually representing the force at the n effector. And then you want to relate the force at this n effector with the joint force. With the joint, the joint can be a revolute joint. So the revolute joints will actually comprise of both force as well as torque. So essentially, eventually we want to establish the relationship between the joint torque and the resultant force and moment applied at the n effector endpoint. So first of all, we see how we can actually derive the basic equation that govern this statics behavior. It's a static behavior because we're actually assuming an equivalent position, equivalent configurations. So we consider an individual link of an open kinematic chain. So just now we have gone through something like this for the DH notations. So we have this link I, and this link I is actually connected to link I minus 1, I plus 1, and link I minus 1. So they connected to these two links via a joint. So we have the joint. We have one joint over here, and then we have another joint over here. So this is joint I plus 1. This is joint I minus 1. We have a base frame that's actually all of these are actually we refer to a base frame. So you have your OO, XO, YO, ZO. So for this link is for this particular, we look at the first joint. So the first joint will have this force. We have a moment. So this moment is actually represented as Ni minus 1I. You also have you also have a force, a reaction force, which is your Fi minus 1I. So on the other side of the joint, you have this joint I plus 1, and you have this I plus 1. So this is the Ng over here is your centroid. So the balance of force will actually tell you that if you're considering only the linear force Fi minus 1 for this link for this joint I minus 1, for this joint I, you will be balanced off by this Fi plus 1, and then the gravitational force Mig. So the balance of linear force will actually look at the free body diagram itself. You will actually give you the Fi minus 1I minus Fi plus 1 plus Nig equal to 0. So this all of these vectors are actually expressed with reference to this base plane. So this you have this balance of linear force. Next, we look at the balance of the moment. So a moment is essentially equal to distance multiplied. So for example, if I have a pivot point, this is a bar. So if I have a force that's actually pointing down, this is the distance. So the force times distance will actually give me the moment. So the moment and torque are essentially very much the same. But a lot of time when we actually refer to something as torque, because there's a rotation angle involved. Okay. So in this context, we have they are essentially the same. So we have to look at the balance of moment about this centroid Ci. So when we actually look at this balance of moment, you have this Ni minus 1I, and then you have this counter force, reactional force, which is your minus Ni plus 1. So we know that the moment is also due to the distance multiplied by the force, the linear force that's actually applied at the end. So your Fi minus 1 will contribute a moment. So you need to determine the distance r. So for example, this distance r will actually be equal to your Ri minus 1I plus Ri Ci. So this plus this will actually give you this vector. So you this vector multiply with this vector, cross this vector itself will actually give you the moment. And then same thing, your minus Fi plus I plus 1 will also provide you with another moment. So this will actually be equal, the minus Fi minus 1 cross the I Ci, which is a distance over here, with respect to the centroid, will contribute this another set of moment. So we all with respect to the distance from the centroid. So when we talk about the balance of moment about the centroid, we can actually form this equation. So when you put all of them together, we have two set of equations, and then we can describe them in the following form. So the Fi minus 1I, Mi minus 1I are called the coupling force and moment between the adjacent joint I and I minus 1. So if I have all these two equations, I will be able to derive all the link except the base link, because the base link itself, basically you don't have the I minus 1. So you end up with two M vector equations. So the number of coupling force and moment involved will be 2m plus 1. So meaning that the two of the coupling force and moment must be specified for the equation to be solved. So we look at how we are going to solve this. We are going to determine this force and moment. So the M force and moment, we specify it using a capital F. So this capital F is a vector that comprises of Fm m plus 1 and N m plus 1. So the Fm m plus 1 is the linear force. So it's your linear force. So this is your linear force, which is Fn m plus 1. And then you have this is your torque or moment, which is your Nm m plus 1. So if you look at the n effector force, it's actually a 6x1 force vector. So this capital F is a 6x1 m-point force vector. Okay. So after you have specified this, you want to determine the relationship between the input torque exerted by the actuator and the resultant end-point force. So in this case, instead of saying moment, we put torque because it's an actuator, so it's going to have a rotation angle. So we tend to use the word torque in this case. So you assume that every joint is driven by an individual actuator that exerts a dry torque of force tau I between the adjacent link, and then you assume the joint mechanism is frictionless. So it's an ideal situation, there's no frictions. So for prismatic joint, the tau I will actually be a linear force exerted along the I joint axis. So you have there's only a single degree of movement. So you have this same thing, you have this linear force, and you have this moment along the joint. So the tau I is essentially a cross of the bi minus 1, which is along the axis, the turning axis, with the linear force. So the bi minus 1 is a unit vector pointing along the I joint axis. So this is for the prismatic joint. And then after that, for the revolute joint, you have so you can actually, if you look at this, you can actually see that the A, if you have a vector A transpose multiplied by B, you are essentially doing a dot product. So this is essentially a dot product. So for the revolute joint, you have the tau I to balance the coupling moment Ni minus 1. So your tau I is actually equal to your Bi minus 1T and I minus 1I. So you have the Bi is again along the joint axis. So again, so you have two different tau. So you have a tau I that's actually based on if the joint is actually a prismatic joint. You have another tau I if the joint equal to Bi minus 1 transpose dot Ni minus 1I if it's a revolute joint. So they are essentially different. A prismatic joint, you only have a linear force, and the revolute joint, you have this moment. So we state the theorem that if the joint mechanism are frictionless, so everything is smooth, the joint torque tau that required the joint torque tau, also known as the equivalent joint torque, corresponding to the end-point force F, will be given by tau if is equal to J transpose F. So this is the Jacobian metric that we have derived earlier last week, but it's a transpose of the Jacobian metric. We state the theorem before but we need to prove that this relationship is going to be true. So the Jacobian matrix is a 6 by M manipulator Jacobian matrix. So there are six rows, and every column is actually corresponding to the joint. So the Jacobian matrix will actually relate the very small joint displacement dq to the very small n effector displacement dp. So you have your dp equal to j dq. We are going to prove this using the principle of virtual world. So when we talk about the virtual world, that is essentially imply a virtual displacement. So virtual displacement at the individual joint. So we have this delta qi, and the corresponding virtual displacement at the n effector, which is your delta xe and delta psi e. So when the delta over here, the delta di, qi, delta psi e, delta xe, delta psi e, they are all very small. So they are in very small displacement. So they are virtual displacement and not the actual displacement that we are looking at, because they are conformed only to the geometrical constraint of the system and obey no other rules. So they only follow the geometrical constraint. So they don't follow any other physics rule. Okay. So I have my joint torque Ti. So Ti is equal to 1 to n, and the endpoint force momentum, endpoint force and will be minus n plus 1, and minus n plus 1. So you actually the n plus 1, there's the link actually end at n, but we have n plus 1 to actually assume that there's something that's actually go further ahead for our computations. If we have the virtual work will actually be equal to your tau I multiplied by your theta qi, and tau 2 multiplied by theta q2, and so on. And then this contribute the part of the thought, and then is the final when it's equivalent, the delta W, the virtual work done will actually be equal to 0. So meaning that the work done at every joint will be equal to the work done at the n effector here. So the work done at the n effector will actually equal to your Fn plus 1 transpose delta xe and minus nn plus 1 transpose delta psi e. So this is from the n effector, this is from the joint. So at equivalent, the virtual work done will actually be equal to 0. So when they're equal to 0, we can actually rearrange this equation into a matrix form. So the tau 1, tau 2, tau 3 can actually be represented as a vector tau, and then the delta Q can actually be represented as the delta Q1, Q2, and so on can actually be represented as a vector delta Q. And then you have your F for the n effector, and then you have your delta P for your delta xe and delta psi e. So with that, you can actually sum them up into this equation. So at equivalent, this will be equal to 0. And then we know that the delta P is actually equal to your J delta Q. So we have delta P is equal to your J delta Q. Okay. So very small p is equal to your J very small q. So you substitute this p with this J delta q. So if you can actually sum them together, you can actually rearrange them together. So this will become your tau minus J transpose F transpose delta Q. We put everything, we single out delta Q and then put this, and then put the delta T minus FTJ. So you actually end up with this. So when you actually end up with this at time, you know that the delta Qs are consist of all the different joint parameter Q1, Q2, and so on. So they are independent. So they are not necessarily equal to 0. So in this they are independent elements. So for this to be equal to 0, the tau minus JTF must be equal to 0. So the tau minus JTF must be equal to 0. This is why you have your tau equal to JTF. So this proves our theorem. Okay. So you can use the theorem that we have proven in an example. So, for example, we look at this. We look at this 2 degree of freedom planar mechanism manipulator. So this 2 degree of planar mechanism, there are 2 links, 1, 2, and then this is actually touched on the it's actually in contact with the surface. So this is the M force, which is your F equal to Fx, Fy. So you apply, so the N effector actually apply a force over here. So you want to find the equivalent joint tar. So this is comprised of 2 joints. So you only have tar 1 and tar 2. A transpose, we give a transpose over here because we say that we basically represent the position, force, everything as a column vector. So you assume that the joint mechanism are frictionless, there's no friction in between them. So you first obtain the Jacobian matrix. We have gone through how to obtain the Jacobian matrix for 2 degree of freedom planar joint, planar manipulator. So the Jacobian matrix will be J is equal to minus L1, X1 minus L2, X1, 2, and so on. So this is the Jacobian matrix. So I believe everybody know what is this X1, 2, right? If you are not, please look at the identity, the trigonometric identity is actually spelled from there. So please, please look at, please look at this trigonometric identity. Actually, these are all the rotation metric. And then you say that if you have a C1, 2, meaning that cosine theta 1 plus theta 2. And then sine 1, 2, meaning that you have sine theta 1 plus theta 2, which is actually your cosine 1 S2 plus sine theta 1 cosine 2, theta 2. Okay? Okay. Yeah, so this, all that you need is only this single sheet of trigonometric identity. You don't have to remember it because you don't have to remember it for the exam. So it's open book. Just one sheet of paper. Then the equivalent joint torque is your torque tar equal to J transpose F. So J transpose, meaning that it will be 1 minus L1 X1 minus L2 X1 2 minus L2 X1 2 minus L1 C1 plus L2 C1 2 my L2 C1 2 will be equal to L1 C1 plus L2 C1 2 L2 C1 2. It's a transpose. So the row become column. Okay, it's your transpose. Simple. So all that you need to know is the Jacobian matrix. There will be a situation when you have your theta 1 is actually equal to 0 and theta 2 is equal to 0. So when your theta 1 is equal to 0, theta 2 is equal to 0, meaning for example, in this case, meaning that your arm is fully extended. So it mentioned that when your arm is fully extended, you have a singularity conditions. So if you substitute the theta 1 equal to 0, theta 2 equal to 0 to these equations, you will find that the tar 1, tar 2 is equal to 0, L plus 1, L1 plus L2, 0, L2 multiplied by Fx, Fy. So tar 1 is equal to L1 plus L2, Fy, and tar 2 is equal to L2, Fx. So if you look at this with the tau, you can actually find that the Fx actually is not present. So meaning that anything in the Fx, the linear force direction along the x-axis, have no torque. So the Fx does not require any torque. when you actually have a situation where your arm is fully extended. We mentioned last week that when your arm is fully extended in this manner, you have a singular condition. We'll have a break for 15 minutes and then we'll continue. If you have any questions, please feel free to come down.
slides?
Yes, I will. Yeah, I will upload the revision slide. I will upload the revision slide, so no need to copy or anything. No worry. Yeah. So I'll upload the revision slide. So anything that I actually find that is important, I'll upload. Yeah. I mean, not that other things are not important, but yeah, if those things are merely elaborations. Yeah. No, we still have a break until we still have 10 more minutes for the break. Yeah. But since today is the last lesson, if you have any question, please feel free to come down to me. Yeah. So I've been seeing many students. I mean, we start off with more than 100 over students, and now we actually have less than 90. So it's about 89, 90. Or maybe 90, exactly 90. So actually it's not that difficult. This module is kind of new. So but on the other hand, you come in to learn new things. Yeah. Okay. Yeah. I'm trying to request for some TA support. So it's still depending on the department approval. So if there's a TA, maybe you can actually approach the TA if you have a question. we'll resume the class. Yeah, thank you. Yeah. It just come to my mind that tonight is the eve of the Valentine's Day. Yeah, so okay. Well, okay. So we move on. We move on. We move on to examine the duality of the instantaneous kinematics and the statics force relationship. We have gone through this. We have come to the mapping on the top of this figure before last week. So we have gone through this. We have gone through this mapping. This mapping actually represent the instantaneous kinematics. So we have your nj, we have your joint space, joint velocity space, which is your joint q dot, which is actually belong to your Vn. The n over here refers to the number of joint. To the endpoint, to the endpoint velocity. So the endpoint velocity is represented as p dot, so belong to Vm. So they are mapped. So we can actually map the joint space with the endpoint velocity space via this Jacobian matrix. So this J over here will map this to this. So for every joint velocity itself, you actually map to this particular space, which is called your Rj. So the duality, meaning that we're actually going to look at how this Jacobian, the transpose of the Jacobian, will actually be how we can actually use it to describe the static force relationship. So the static force relationship, we are now looking at the mapping of the n effector endpoint and then effector force, the capital F, which is belong to Vm, be mapped onto the joint top, the tar belong to Vn. So from last week's lecture, we know that for the linear mapping of the instantaneous kinematics, there's a range space Rj. So this is the range space Rj. The Rj stand for the set of all possible n effector velocity generated by the joint motion. So you have this range space. Bear in mind that for the instantaneous kinematic, the mapping is actually from the joint space to the n effector space. So from here to here. So this is a range space Rj. So when the Jacobian matrix degenerate, so meaning that the arm configuration is singular. So for example, if I actually extend the full arm, so this is a situation of singular. So the range space will not be able to span the whole vector space Vm. So it doesn't cover the whole vector space Vm. So you actually see the empty space over here. So there will be a direction in which the n effector cannot move. So your p dot is equal to, when your n effector cannot move, meaning that your p dot is actually equal to 0. Your velocity is equal to 0, and then at this particular point itself, it will actually corresponding to this pace. So you have situations. The nj, which is known as the null space, is a set of the joint velocity that do not produce a velocity at the n effector. So for any q dot that actually belong to this space, there will be your p dot will actually be equal to 0. So meaning that you still have your q dot, but what happened here is the n effector have no position. So we actually illustrate this by, for example, saying that you can hold on to a water bottle, and then you constrain it, but you can still move your joint. And a more common example would be to put your hand on the table, and then there's no movement in your n effector, so you're not constrained by anything except your cell world, but you can actually turn your joint. So n effector have no force, n effector p dot equal to 0, but your joint is actually having a velocity. So for the mapping of the statistics, which is the bottom here, we have something similar, but the mapping is actually in the other directions. So the mapping is actually from the m dimension vector space, the Vm, associated with the n effector. So this is associated with the n effector to the nth dimensional vector space that's actually associated with the joint. So you can actually see the reverse mapping. So the joint tar can always be determined uniquely for any arbitrary endpoint force F. So meaning that the tar can always be determined, or from all of these we're able to map onto a space over here. So if I have a given joint torque, the endpoint force does not always exist. So this, for example, the endpoint, there's a certain set of joint torque, there isn't an endpoint force. So this endpoint force is actually known as the null space J transpose. So it's representing the set of all the endpoint force that do not require any torque at the joint to bear the corresponding load. So I have gone through an example earlier. We have a full arm expanded. So one of your force F actually doesn't require any joint force. So the endpoint force is actually borne entirely by the structure of the arm linkage. So with this, you actually link to the topic of compliant, stiffness of the manipulator and compliant. So because of time constraint, we are not going to go through this in this module. So you have your range space Rj transpose, representing the sets of all possible joint torques that can balance the endpoint force. So you have this bin 0, the null space, and you have this njt that represent the null space that actually go to a certain range space Rjt. So if we actually combine the two things together, we can find some interesting linkage. So the null space Nj is complement to the range space Rjt. So they are orthogonal complement. So meaning that if I have a non-zero vector x in the Mx, it cannot also belong to J transpose, and vice versa. So the blue color here indicate the direction which the joint velocity do not cause any n effector velocity, and the joint torque cannot be balanced with any endpoint force. So this is actually represented by the blue line. And then the range space Rj will be orthogonal complement to Njt. So this is represented by the red line. So the no joint torques are required to balance the endpoint force when the external force act in the direction in which the n effector cannot move by the motion of the arm joint. So you have this duality of the relationships. So the study of the duality of the relationship will come in handy if you want to actually study a compliant mechanism. We take a step back and consider two frames, C and B attached to a rigid body. So if I have a B frame, C frame, and then both frames are actually referred to this frame A. So if you are given the AFC, meaning that the force at frame C, we refer to frame A, and then you are also given the A and C. So meaning that these are essentially force and moment at C expressed in frame A. You want to determine the force and moment at B if the force and moment is actually known as C. So you have a situation given here. So this is important because, for example, for a lot of time, you have your tools, and then your force and torque sensors is actually present in C. So you have tools that's actually making contact with the surface that you're actually acting on, and then your sensor is actually on the end effector. So your sensor at the end effector, you will be able to, you have your force sensor reading, but your primary interest is actually the force that's actually touched, in contact with the surface. Because you don't want to break the surface. You want to know the force that's actually acted on the surface that you're dealing with. So how do we actually determine that? Same thing, we look at the reaction force moment applied at B under equivalent. So we do the free body diagram. So you have we have this, we introduce this AFR, which is the reaction force. So the R stands for reaction force. So the reaction force is equal to minus FAB. And then you have this AMR equal to minus AMB. So this is the reactional force and moment at B under equivalent. So they should be balanced. And then at the same time, you also have this ANC, AFC. So remember we mentioned that the C is actually where you're going to hold the sensor. So you know what is actually given at the C. So for equivalent, in equivalent position, all the sum of force is actually equal to 0. Sum of linear force is equal to 0, meaning that your AFC plus the AFR, the reaction force, is actually equal to 0. So your AFR is equal to minus AFC. So if you know that, you also know that the AFB is equal to minus AFR, so your AFB is equal to AFC. So meaning that your AFB is equal to your AFC. This one follow? Okay. And then the sum of moment about the origin of C. So the C is remember the C is your sensor position. So it could be your width also. So you want to take reference with the C. So you want to take reference with the C, the sum of moment should also be equal to 0. So over here you do the mechanics. So you have your AMC. You have your AMC plus APB. So APB meaning that is the vector from A to B. This point, this is APB, and this is APC. So APB minus APC cross AFR. Okay, so you know this is APB, this is APC. So plus the AMR should be equal to 0. So from here you will be able to determine that the AMR is equal to this. So your AMR, you also know that you have defined AMB is equal to minus AMR. So your AMB is equal to AMC plus this. So this can actually be simplified as AMB equal to ANC plus APC cross. So this is a symmetric metric that we actually taught when we first in section 1 of the chapter 2. The symmetric metric that we taught. So in metric form, this AB, so if you actually sum it up, the AFB is essentially equal to AFC. So this is, you can write them in metric form in this manner. So AFB multiplied by identity metric 0. And then the AMB is your APBC cross. So APC cross is the same as your ABPC cross. So in a typical application, we would like to relate the C with B, because in this case, you are actually relating with the base frame. But your sensor is actually with C, and your interaction force is with B. So you actually want to relate this with the sensor force. So you cannot stop here. You need to move on. So you need to move on by expanding this. We know that AFC, ANC is equal to the ACR multiplied by 0 ACR multiplied by ACC and CNC. So basically you multiply the matrix and then you have the C. So you have the C and C cancel off. You have this C and C cancel off. So this is, you have your AFC. You have the C and C cancel off. You have the ANC. Okay. So you substitute this into these equations. Into here, you end up with this. You do the multiplication itself, you finally end with this matrix. Okay. You also know that the BFB is equal to your BAR AFB. So same thing, you can visualize that, you can cancel off this A. So this is essentially your BFB. And BMB is equal to your BAR AMB. So the A and A cancel off, this is your BMB. So you can also express the BFB, BMB in this form. So with that, you end up with these equations. Okay. So when you put everything together and expand on this, you will find that this is your transpose ACR. This is the same as a cross of ABR BPC cross ACR CFC. So basically you take this and this cross this thing. You have your BAR. So your BAR cross this, multiply with this one, and multiply with this one. And then you have this one cancel off, so you have your BPC cross BCR CFC. So finally you actually end up with your BC cross BCR CFC. So this is your final equation. So what happened now is you are actually relating the force, the interaction force at B of your end effector of the two with the sensor force at C. So what is this matrix? You can look at this matrix by looking at this example. So another way of looking at it is I'm using the force sensing width. So this is your C, this is your B. You have the sensor frame being attached in this manner. So the force and torque applied at the two tip is your F torque, is your TF. Your SF is the output of the sensor. So the output of the sensor, so it's your FNT. So if you're given a transformation metric STT, relating the S to T, relating the sensor to the frame T. So this is where you have the sensor, this is your width. So this is your frame, you may consider this as your frame A, B, and this is C. So you have the fourth moment vector from S to T will be given by TFT is equal to TS, TF, SFS. So you cancel off, this is your T. So this is a transformation matrix that's actually in between them. So this is actually equal to this. Okay? Any question? So this is a symmetric matrix that we talked about earlier. I'll upload a slide. I'll upload the composition of this matrix. It's a symmetric matrix. So basically this is this matrix. Sorry, did I have the matrix? basically is this matrix, but basically is this matrix. So this is this, but over here you have your P rather than instead of the omega. Okay. So this is this one. It's the same as this one. Okay, your symmetric matrix multiplied by BCR. So in summary, we have studied the expression for translation and angular velocity. So it transforms the velocity in different space. So we relate. So this is the session 1, and then after that we talk about the computation of a geometric matrix that relate the joint velocity with the n effector velocity. We used to solve, and then we can use it to solve the forward and inverse instantaneous kinematic. So we want to understand the concept of Roberts singularity, and then we want to study the static force and torque transformation between task space and the joint space. And then the static force torque transformation between the frame. So this is where you have your sensor frame and the tool frame. We're not going to talk about the stiffness of manipulator arm. So you should know that when the force is applied at the end point of the arm will defect by the mouth depending on the stiffness of the arm and applied force. So this contributes to the study of compliance in the robotics. Okay? Move to the last topics. Okay. Move the last chapter, which is relatively smaller, shorter chapter. So it's about robot trajectory planning. So when we talk about trajectory, we essentially looking at the time history of the position, velocity, and acceleration of each degree of freedom. So from this definition itself, we will know that we are going to look at the joint space. So every degree of freedom will actually corresponding to one joint. So, for example, a robot robot manipulator has 6 degrees of freedom. So, meaning that there are 6 joints. So, every joint itself has a certain position. So, if it's a revolute joint, you have your theta, and velocity, which is your theta dot, and then acceleration will be your theta dot dot. So, meaning that we want to know the position, velocity, and acceleration of every joint. So what the user did is it will simplify, it will specify the desired goal position and orientation of the n effector, and then the system will actually decide the trajectory. So for example, if I'm going to draw a circle, I specify A, B, C, and D, and then the system should actually generate the trajectory for me from A to B and B to C. So A to B is a segment, B to C is also another segment. So we want to have a smooth path. So a smooth path, the definition of a smooth path is meaning that it should be continuous and have a continuous first derivative and then even a continuous second derivative. So if I do not have a smooth path, if the motion is rough or jerky, it will actually increase the wear and tear of the mechanism. In some cases, it may not meet the requirement of the applications. So when we talk about the smooth path, we are dealing with the continuity in mathematics. So this is only for your information. So when we talk about continuity, there's something called a geometric continuity. So a geometric continuity, G0, implies that the 2 segments are connected. So 2 segments are connected. So this is 2, 0. When I have G1, meaning that the two segments will have the same tangent. When I have G2, meaning that I should have the same tangent as well as the same curvature. So same tangent, and then I have the same curvature. So yeah, so there are three class of geometric continuity. But what matters to us most is the parametric continuity. So a parametric continuity meaning that if I achieve a C0 continuity, so the C0 is the same as your G0. So meaning that the two segments are connected. So when I have the same C1 continuity, meaning that both segments should have the same velocity vector. And then if I have a C2 continuity, I should have the same velocity as well as the acceleration vector. So if I define my positions, if I'm referring to a joint, the position as theta, the angular positions as theta, so the first derivative will be theta dot, your velocity. The second derivative will be your acceleration, theta dot dot. So when I talk about smooth path, we are actually related to the studying of the continuity in mathematics. So the path shape we essentially describe in terms of the function of joint angle. So the first thing is you need to identify the path points. So the path point will include all the y point or waypoint plus the initial and final point. So for example, if you're going to draw a 0, so your A and B, you may consider your initial point is A, your final point is also A, and in between the point will be B, C, and D. So the by point will be located midway between the starting and stopping position of a robot tooltip. So the tooltip must actually pass through it without stopping. Or you can actually define it as AB as one single segment, and then you are going to stop at A before you move on. So you need to identify the path point, and then you need to identify and then you have to determine the desired position and orientation of the tool frame relative to the station frame. So you need to, and then from there you need to use the inverse kinematic to determine the set of desired joint angle. So you have so for example, if I'm going to have my arm hold the robot in this manner, hold the water bottle in this manner, so this is the different joint. Okay, so I need to know the joint angle. And then after that, you generate a smooth function for each joint. So meaning that if I'm going to move this water bottle from here to here, so I theta equal to 0 to theta equal to 90 degrees. So I need to generate the trajectory point. The trajectory will actually be expressed in terms of the theta dot, and theta double dot. So the joint space scheme will achieve the desired position orientation only at the right point. So there's discrete corresponding between the joint space and the Cartesian space, so there will be no issue with the singularity. So every joint space will actually correspond to a Cartesian space. So one way of achieving it is using this cubic polynomial. So you want to move the tool from its initial position to a goal position in a certain amount of time. So for example, I want to move this from here to here, to right angle in a certain amount of time. I calculate the initial and goal points and position and orientations, and then after that, I adopt a smooth function to interpolate every joint value. So one way of interpolating the joint value is via cubic polynomial. So you are plotting, you are plotting, so in this plot, you are plotting the theta, that means the joint angle versus time. So this is your TF, this is your T, so this is your, the x-axis representing your time, the y-axis representing the angle. So you are plotting the angle versus the time. So you are given the initial angle and the end angle, as well as the time that is actually going to achieve it. So your theta 0 is your initial position, initial theta, and your theta f is your end theta. So imagine if you're going to have a 6 joint, going to have 6 DOF, 6 dot manipulator, you will have 6 set of theta. So we focus on one specific set of theta. So you have your theta. So this is your initial position. Your theta 0, meaning the 0 meaning that t is equal to 0, is equal to your theta 0. Theta tf, at time tf is your final position. You have your theta f. And then your initial and final velocity will be theta dot 0 is equal to 0. Theta dot tf is equal to 0. So meaning that you're starting from 0. You're starting from 0 velocity, starting at rest, and then when you come to a final position, you should also be at rest. So this interpolation can be approximated by a cubic polynomial. The word cubic over here actually implies a third-degree polynomial. A third-degree polynomial function will be your theta t equal to a0 plus a1t plus a2t squared plus a3t cubed. Okay? So this is your equation 2-1. So if you do a differentiation with respect to t, you have your velocity. You have your joint velocity. So your voice velocity will be theta dot t equal to a1, because this one differentiate, this is gone. So you have your a1, 2a2 t plus 3a3 t squared. If you differentiate again, you have your acceleration. So you have theta dot double dot t equal to your 2a2, 3 times 2a3 t. So you have your 6a3 t. So you have 3 sets of equations. And then you have your 4 constraints. You have 4 unknowns. So you have your A0, A1, A2, A3. So you need to determine your A0, A1, A2, A3. So in this case, we actually assume that the joints start and finish at T3. So how? This is good, yeah. Okay, so you have these cubic polynomial function. You do the differentiation, you have your theta t, theta dot t, theta double dot t. So this is a differentiation that we have gone through. We have 4 equations because of the 2 constraints, the 2 set of boundary conditions. So when t is equal to 0, your theta t is equal to, your t is equal to 0, so is your theta 0 is, so everything is 0 over here. So you know that your theta 0 is actually equal to your A0. And then after that, you look at your theta dot t. So when t is equal to 0, your theta dot t is also equal to 0. So your theta dot t is equal to 0. Your theta dot t is a1 plus 2a2t plus 3a3t squared. So this is 0, this is 0. So you know that your a1 is actually equal to 0. So this is the first set of boundary condition. two equations. And then when your t is equal to tf, so your theta f is equal to your theta f. This is theta tf. Theta tf is equal to theta tf. So your theta tf is equal to theta 0 plus a2 theta t square plus a3 theta ta3 t fx f cube and so on. So you do the mathematics, you will know that your a2 is equal to theta f minus theta 0 divided by tf square minus a3 tf. And then you also know that the other boundary condition is at n point, your theta dot f is also equal to 0. So same thing, you have this a3 equal to minus 2a2 3tf. So you put the 2 into 1, you will have your a2 equal to 3 theta f minus theta 0 divided by tf square. And then once you have the 2, you put back onto, once you have a2, you put back into a3, you will find that the a3 is equal to minus 2 tf cubed theta f minus theta 0. Okay? So this is how you have these four, this is how you have determined the four parameters, the four constants for these equations. So in some cases, the path specification may actually include the intermediate y point. So the intermediate y point or waypoint. So the desired velocity of the joint at the point may not be actually equal to 0. So this point may not be equal to 0. So you have some constraint over here. So you've used a cubic parameter for each segment. So you know that your theta dot 0 is equal to theta 0 dot. Your theta dot tf is equal to theta dot f. So you have your, but the theta dot in the midpoint here need not be actually equal to 0. So the y point meaning that you must, your angle must actually pass through here. It's the theta that's actually passed through here. It doesn't actually mean that your end point will have to pass through here. Okay, so because this is a plot of theta over t. But a combination of your theta will actually ensure your end point reach the waypoint that you actually want to reach. Okay. So if you apply the position and velocity constraint at the equation 2.1 and 2.2, which is these are equations, you will be able to find this A0, A1, A2, and A3 respectively. So the question here is, how do we actually specify the joint velocity at this waypoint? So you need to specify the desired velocity at every waypoint. So this is a waypoint. This is a waypoint, and then apply the inverse kinematics. Inverse Jacobian. So there may be a singularity issue here. So remember the Jacobian that you actually need to do. So the system can actually choose the velocity at the so you can specify via two methods. One way is to do this. So this is not so straightforward. And actually I'm hoping that you can actually do this for the CA. The other way is actually choose the velocity at the waypoint by suitable heuristic. So the simplest heuristic is actually to specify the velocity. Is to specify the small 9 segment. So, for example, if I specify this straight 9 segment over here, actually represent the velocity. So this is the velocity tangent to the curve at every waypoint. If the slope of this line actually change the sign, so that means from going up to going down, from going down to going up, you choose a 0 velocity. So meaning that you stop and then you change the direction. So if the stroke of this line do not change sign, you choose the average of the two slope as a y velocity. So for example, in this case, from here to here, there's actually a change sign. One is going up, one is going down. So you set, so this must be 0. This is one heuristic. You must stop first before you can actually change. And then, but what happened here is, for example, if you're going from here to here, so this is continue going up. So this speed will be the average of these two speeds. So this is a simple heuristic that you can actually play with without determining the inverse Jacobian. So you can actually have this 5 degree of freedom polynomial. So you have your theta t equal to a0 plus a1t plus a2t squared plus a3t cubed plus a4t4 plus a5t5. So you have 6 constraints. You know the initial and final velocity, position, velocity, as well as the acceleration. So you will be able to the 5th order polynomial, you can actually specify the constraint. Say you can actually specify the constraint, for example, 0 for your acceleration at the start and end point. So the higher order polynomial will be smoother compared to the 5th order polynomial will be smoother compared to cubic order smoother. So if you have previously you have the initial and final position and initial and final velocity. Now you have your initial and final acceleration as well. So that altogether you have your 6 equation, and then you have your 6 unknowns. So your a0 to a5. So if you do the max, you will be able to find this parameter. We look at an example on cubic polynomial trajectory generation. So this is a textbook example. So if I have a single link robot, we are revolute joint, motionless at theta is equal to 15 degrees. So I only have one joint. So this is only a one single joint robot. So there's only this single joint. So you have multiple joint. You have to coordinate the joint, all the different joint motion. So you start at 15 degree. So this is 15 degree, and then you are supposed to move the joint in a smooth manner to 75 degrees. So this is 75 degrees. So from 15 to 75 degrees. And you're supposed to do it in 3 seconds. So 1 second, 2 seconds, 3 seconds. So this is your plot of theta over t. This is your plot of the position of the joint as a function of t. And then you're supposed to find the cubic coefficient for this motion. The manipulator rests at the goal point. So it's supposed to stop over here. So from here itself, you can actually, from this finger plot itself, you can actually plot the velocity as well. So it's supposed to be smooth. So your velocity is supposed to, from 0, is supposed to pick up, and then you peak, and then after that peak at the midway point, and then after that you should decelerate. You should slow down, and then you should slow down, and then so that eventually your velocity equal to 0. You should do this in a constant acceleration. So this is the plot of your acceleration. So constant acceleration down. This is all joint. So same thing, you know your a0 is equal to theta 0, a1 is equal to 0. You have the cubic formula that we derived earlier. So your a0 is 15, a1 is 0, a2 is 20, a3 is 1 minus 144. So you can calculate your theta t. You can calculate your theta dot t and theta dot t. So if you with the a0 to a3 determined, you can have your theta t. So with that, you can you have your theta dot t as well and the theta dot double dot t. So you can actually plot them together. You will actually see you will actually see the shape over here. You'll see the plot over here. Okay. This one's simple. So you have a single joint angle, and then from one position to another position. So from 15 degree to 75 degree. So you need to achieve it in a smooth manner. Okay. So we talk about the cubic polynomial function. The next which is a curve. You can also have a nice segment with parabola plane. So the path shape is linear. So for example, if I'm going to go from theta 0 to theta f, I want to do this in a constant velocity. So this is a straight line, it's a constant velocity. So theta f minus theta t over the time is a straight line. So this is constant velocity. So you assume that the theta dot t0 is equal to theta dot tf is equal to 0. So at these two endpoints, you are going to stop. So the question here is you need to find the initial, you need to find the ramp up from t0 to this point, and from this point to tf. So because you can't straight away go to this constant velocity, you have to start from 0 and then to reach this constant velocity. And then they have to be smooth. So smooth meaning that you should at least have a C1 or C2 continuity. So you need to determine this parabola and this parabola. Same thing if you want to go from a certain velocity to stop, it should also be smooth. You should at least have your C2 continuity. So you need to determine this thing so-called the parabola plane at each point path to ensure a smooth path with continuous position and velocity. So when I actually form this whole full thing, this is continuous, and then you actually achieve a C1 continuity. So how do we actually determine this plane in ring? So you may actually consider a constant acceleration. So a constant acceleration meaning, so for example, from T0 to T1. So T1 is the start of your linear segment, and T2 is the end of your linear segment. So when you have a linear segment over here, meaning that your velocity is constant. So this is your velocity is constant, and then from theta 0 to theta b, you have a constant acceleration, and then from here to 0 you have a constant deceleration. So this is the plot of your theta. This is the plot of your theta dot. And then the same thing. Yeah, you want a constant deceleration. And then you actually assume that you want to have the constant acceleration, and the constant deceleration have the same magnitude acceleration. So that means the magnitude is the same. That means you have the same rate of acceleration. But of course, their signs are different. So one is deceleration, one is acceleration. So if you actually look at this itself, you know that the T1, if you look at this graph, you know that the T1 minus T0 is equal to your Tf minus T2 is equal to your Tb. So this is the same time, although the graph doesn't actually draw to scale. So meaning that this acceleration time and the acceleration time is the same. So you You also indicate a halfway point mark position, which is your theta h. So this is actually at the halfway mark, which is your th. So your theta h is equal to theta th. Your theta h is actually equal to your half of your theta f plus your theta 0. Th is the half of the Tf plus T0, so it's at the midpoint. So at the midpoint, you take the initial point plus the end point divided by 2, so you get the midpoint. So if you know the starting and end position, and you're assuming T0 is actually equal to 0, you will find that there's actually many possible solutions. So if you assume a certain Brand acceleration, so you're supposed to find TB. So you're given a certain Brand acceleration, so you actually know that you're going to accelerate at which particular point. So meaning that your theta dot b is equal to your theta dot b, theta 0 dot plus your theta double dot tb. So this is the same as taking your th minus your th minus your tb, your theta b, theta h minus your theta b divided by your th minus over your tb. And then you know that this is going to, the theta 0 dot is going to be 0. So your theta h is equal to your theta h has been given as a theta f plus theta 0 over 2 over here. And your th is half because your theta t0 actually start from 0. So you can actually determine the theta b will be the end of the Brand region, and tb is the duration of your parabola Brand. So because you want to assume that the velocity at this first Brand region is actually equal to the velocity over the linear region. So this is common. So you know the linear region. So your theta b will be equal to theta 0 plus half theta double dot t2 tb square. So this theta dot is a common acceleration over the Brand. So if you are given this theta 0, the starting position, theta f, the end position, and tf, the total moving time, you can actually get this theta double dot tb square minus theta double dot tfb plus theta f minus theta 0 equal to 0. So substitute and then you got this thing. So after you got this thing, you need to the end thing is actually you need to determine your TB. So you will find that your TB equal to your TF2 minus square root divided by 2 theta dot. So this is again some mathematics. So you know that if I have a as squared plus bs plus c, I will have my x is equal to minus b plus minus b squared minus 4ac divided by 2a. So this is plus minus. So from the previous polar equation itself, so we'll know that this is your. So you have so from there you will know that your TB is equal to, because of this, you will know that your TB is equal to TF over 2 minus your square root of theta dot square TF square minus 4 theta double dot TF, theta F minus theta 0 divided by 2 double dot. So this is from the earlier equation, and then you know this formula. So this is why you have this. So the question here is, you must, so in this case, the TB, so for this one to have for TB to be a valid value, your TB, your square root of theta double square TF square minus 4 double dot theta F minus theta 0 must be greater or equal to 0. So this must be greater or equal to 0. So you do, for this to be equal to 0, this must be equal to 0, and then you will actually find that your theta double dot is actually equal to your 4 theta F minus theta 0 divided by TF square. So this is how you have this. So if you look at this, you see that the theta double dot, the acceleration must be sufficiently high. So if you have equality, so your TB will actually be equal to your TH. So there will be no constant velocity or linear segment. So meaning that this thing will join up over here. And then this thing will come from, so basically there's no linear segment if your TB is equal to TH. So this is quite obvious. So if your TB is equal to TH, so meaning that this is one blend, and then this is another blend, there's no more linear segment. Okay? So if you have to plot the graph itself, it will be something like that. So you have your acceleration and then followed by the deceleration. Any question? Any question? It's not very difficult, so you just have to follow the thing. The whole idea here is actually you want to generate the trajectory. So the trajectory is a function of your theta, the joint angle. So we describe everything based on one single joint. So you have so for a robot with 6 degrees of freedom or 3 degrees of freedom, you will have 3 joints. Okay. So you have the end position, and then you need to compute from there. So there are different methods of doing it. So the first method that we actually talk about is a cubic polynomial function, and then we can actually improve on the cubic polynomial function with a higher degree of polynomial. And then the other way is actually via a parabola blend. So a parabola blend meaning that you have a linear segment and then a parabola blend at the two end, at the start and at the end. You can't start with a velocity, so you definitely have to start from a 0 to achieve a certain velocity. So you can't just have one linear region, just one single linear segment. So same thing. In both cases, we actually talk about the y point. So the y point meaning that the point that the joint should reach. So the joint should have the specific value. So for example, if I have this, I want to generate this trajectory, meaning that I have to connect to this specific y point. So I have this specific y point, which is my theta j, theta k, and theta l. So I start from theta I, and then I end at this particular point, at this time tf. So from theta I to theta j, there's this linear segment. So similarly, I need this polynomial. I need this polynomial blend, and then to move on to the second segment and to come to this waypoint theta k, I need another segment. Then after that, I come to here and move on. So now I have these three. So I specify some constraint that the joint value must achieve. So the deviation is very much similar. You have the we will take one segment at a time. So you are given the djk. The djk over here is the overall duration of the segment connecting point j and k. So connecting this point j and point k, this is the duration. And then the tk is the duration of the blend region at the point k. Tk is this is tk, so this is the blend region. And then tjk is the region for the linear segment. So I need to determine this as well as this. So the speed at this linear portion is theta dot jk. From j to k, this is the linear segment. And then the theta double dot k is the acceleration over here at the blend point. So you have to, this is the acceleration at the blend point. So if I have a constant acceleration, theta double dot k, the two lines over here indicate that this is the absolute value without regarding to sign. So if you have given all the path point, the theta k, and all the duration tdk, and this thing, and then you have the magnitude of the acceleration point, theta double dot k is the magnitude, so there's no sign. You don't know whether it's going to accelerate or decelerate. So you want to calculate the blend time tk, so this is the blend time tk, and the linear segment time tjk. So you want to know these two terms. So if you know these two terms, you will be able to achieve the y point theta j and theta k. So we look at how the calculation will be like. So how the duration will be like. So for the interior point, so presume from j to k, your theta dot jk is actually equal to your theta k minus theta j divided by t djk. So basically, you just take the 2 points. The distance is a constant acceleration. So if you take this minus this, divide by the total time here, you will actually give the acceleration. You will actually give this theta dot jk. Sorry, your velocity. This velocity. And then your theta dot kl, so the kl, same thing. If you take this, the theta l minus the theta k, divide by the total time, the dkl, you will actually give you your theta dot kl. Because this term is essentially the linear portion. So you define your theta double dot k. That means your acceleration over here is equal to the magnitude of the acceleration multiplied by the sign. So the sign meaning that if I take the theta dot kl minus theta dot jk, if the theta dot kl is bigger than my theta dot jk, so meaning positive, so the sign will actually return positive. So the sign function will return positive. If you do the minus, the subtraction, and then this bigger than this, you will have a minus sign. So this is your sign function. So from there, you will actually find that your tk is equal to your theta dot kl minus theta dot jk divided by theta double dot k. So you can also similarly, so you can determine your tk. You can also similarly determine your tj. So your tj, which is over here. So, but in this case, we focus on this. So the duration of the linear segment, the tjk, will be equal to your djk minus half of the tj, half of the tj, because this is the tj. So you minus half of it, and then you minus half of the tk. This is half of the tk. So you have your tjk. This is tj. So half of tj, half of tk will actually give you your tjk. So once you have all these things, you can so this is the representative of all the intermediate segment. As always, you have to take special consideration at the beginning and at the end. You have to take the special consideration at the beginning and the end. So now we actually look at the first segment, the beginning. So the beginning is only T1. So T1, you have your theta 2 minus theta 1, TD1 2 minus half of T1. Yeah, you will have your theta 1 dot about T1. So essentially it's your velocity at the first 9 segment. Theta dot 1 2. So you can easily determine your T1, like what we have done, what you have previously done earlier on. So we start off with the waypoint. So your T1 is the same. So your T12, the T12 is equal to your TD. Again, you need to minus off this one and half of this. You will get the T12. This is your T12. This is half of your T2. Then now you actually look at the last segment. So the same thing, the last segment is you connect your theta n with your theta n minus 1. Sorry. If you have your theta dot n minus 1 n given over here, so essentially this is again the same as what you have done earlier on without the right waypoint. So your Tn minus 1 n is actually equal to this. This is what you have done earlier on without the waypoint. So with that you have the intermediate point, you have the first and end point. You have determined all the parameter blend point for the entire path. We'll look at an example before I end this. So suppose that the trajectory of particle joint specified as follows. You have your 10 degree, 35 degree, 25 degree, and 10 degree. So the duration of these 3 segments are 2, 1, and 3 seconds respectively. So 2 seconds to travel from 10 degree to 35 degree, 1 second from 35 degree to 25 degree, and 3 seconds from 25 degree to 10 degree. The magnitude of the default acceleration at all blend points is 50 degree per second square. So this is your acceleration at all the blend points. So you're supposed to calculate all the segment velocity, blend time, as well as your linear time. So what you did is, you know the Tn is equal to this, so you calculate your T1, and then you calculate and then you know your theta 1 is actually given to this equation. You calculate your theta 1, 1, 2, and so on. So basically apply the equation throughout, and then for the last segment you have these equations. The velocity will be given by here, and then finally you have the 2, 3, and 3, 4. So basically you apply the equations that we have gone through. Okay? And after that, if you want to plot it, you can actually plot it nice. If you want to visualize it, you can actually see it nicely over here. You have your theta equal to 10 degree, 35 degree, 25 degree, and 10 degree. So the starting blend time is 0.27. T2 referring to this particular time. Theta 2 time is 0.47, and from theta 1 to theta 2, the linear segment is 1.5. And then the theta 3, T3 is actually at this 0.098. From T2 to T3 is 0.716, and so on. So this example basically apply the equation that we have derived earlier. So this is quite a short chapter. So basically you only need to know so basically you need to know that you can actually plan point-to-point trajectory in the joint space. So the alternative of the joint space is task space. So there are pro and con for joint space and task space. And then so in our case we focus only on the joint space, and then you can the point-to-point trajectory via the joint space. You can plan the trajectory via the y points. So we basically go through two methods. So one is polynomial functions. So the polynomial trajectory functions will comprise of the cubic as well as a 5-degree polynomial functions. The higher degree polynomial function have an advantage to achieve a more smooth function. But the problem here is actually when you have a higher degree, meaning that it's going to be more computational intensive, so it costs more. The other way is actually linear with the bipolar blends. So you have the blend at the beginning and end point. So all these methods can actually be done with the y point. And then you can also plan trajectory with velocity and acceleration constraint. So meaning that the velocity and acceleration at the specific point can actually you can actually specify a specific acceleration and velocity. So this set as constraint on your trajectory planning, trajectory generation. Any question? Okay. Any question? Yeah. Okay. Good. No question. Yeah. Okay. So that's all for part 1 of the module. So I'll upload the revision slide that I put up, and then I guess that's about all. And then I will also upload the exercise 3. So I will give the solution for the exercise 3 next week. And then please look out for the email on the quiz. If you have any question, please feel free to email me. Okay. Thank you. Yeah. Tomorrow is Valentine's Day, so I wish everybody have a good time. Thank you. Bye bye. Okay.
Say that, oh, you're very good, then you can. Yeah. So if you understood.
We just define the how your question.
It depends on. Why is actually if I join. Actually, there's this is my detailed one. Yeah, because actually